You think you know space? Think again. I want to blow your mind in about 7 minutes on YouTube, 16 by 9. So buckle up. You think you know space? Think again. We're skipping boring lectures and diving straight into the most insane, flashy, and unbelievable facts about the universe. James Webb discoveries, Parker Solar Probe speed records, the subtle thrum of gravitational waves. I'm going to hit you fast, hard, and non-stop with 20 facts that feel like sci-fi but are absolutely real. Stick around, the last fact will change how you see everything. This is high energy, packed and made to spark that same childlike awe I get staring up at the night sky. Ready? Let's blast off. You want scale shock? UY Scuti is a red supergiant so enormous that if you swapped it with our sun, its surface would engulf Jupiter's orbit. Imagine our sun as a tennis ball, UY Scuti as a house. The tennis ball fits inside with room to spare. Its radius is over 1,000 times the sun. Volume? Trillions of suns could fit inside. The James Webb and other telescopes help us measure these monsters by how they shine and how their light stretches. We use brightness and temperature to estimate size. These stars are unstable, live fast, puff off mass, die spectacularly as supernovae, and seed the galaxy with heavy elements. When I say it could swallow your sun, I mean it in the most literal, stomach-turning way possible. Surprise! Black holes aren't cosmic vacuum cleaners vacuuming up everything in sight. They bend space so tightly that light can't climb back out. Picture a heavy bowling ball on a trampoline. Anything rolling nearby falls into that dip, not because the ball pulls with a hose, but because the trampoline is warped. That's general relativity simplified. It explains orbits, gravitational lensing, and why stars circle invisible centers. The first image of a black hole's shadow made this idea visually real. Some are stellar mass, others supermassive, the size of our solar system's orbit. They're governors of local space-time curvature. Gravity is geometry, not suction. Imagine watching the universe's baby photos. JWST has found galaxies so distant their light left when the universe was a newborn. Some push redshifts past Z11 to 13, meaning we're seeing them 400 to 500 million years after the Big Bang. That time travel is not a metaphor. Light is literally carrying history to our telescopes across 13+ billion years. These early galaxies are tiny, intensely star-forming, often blue. JWST's infrared eyes peer through redshift and dust to detect them. Each one rewrites timelines for how fast structure formed and makes the early universe feel shockingly lively. Space can ring like a bell, gravitational waves explained. Space can literally vibrate. LIGO and Virgo detected ripples reaching Earth from colliding black holes and neutron stars. Picture two heavy dancers spinning faster and faster. The floor quakes. LIGO measured shifts smaller than a proton. When the detectors caught those signals, we heard the universe. Gravity's soundtrack revealing mass, spin, distance, and testing relativity. GWW1 FAMES 0914 showed black holes merging. A later neutron-star merger produced light, gravity plus light simultaneously. Parker Solar Probe, fastest thing we made. It's flirting with the sun at jaw-dropping speeds, over 700,000 kilometers per hour at perihelion, faster than any spacecraft. It uses repeated Venus flybys to shrink its orbit and slam past the sun faster and closer each pass, enduring brutal heat. That record is engineering extremism to answer how the corona gets so hot and how solar wind accelerates. In situ plasma and field data tie sun images to the particles that drive space weather. It's a stunt, a science mission, and a record-smashing thrill all in one. A city-sized star spinning hundreds of times per second, the fastest pulsar. Pulsars are neutron stars, sun-mass city-sized remnants. PSR J1748 2446 AD whips around about 716 times per second. Imagine a steel ball the size of a city rotating hundreds of times each second. Physics at the edge, spun up by accreting material in binaries like a cosmic top. Their regular pulses are precise clocks in labs for extreme nuclear physics. Magnetars have magnetic fields a trillion times Earth's. Get close and your credit cards would erase from the field alone. Their surface fields reach 10 to the 14, up to 10 to the 15 Gauss. Magnetic stress fractures the crust, unleashing giant X-ray flares and gamma bursts detectable across the galaxy. They can tweak Earth's ionosphere from thousands of light years away. Exotic matter and quantum electrodynamics, terrifyingly beautiful. Not every planet has a star. Rogue planets wander the galaxy, ejected from systems or formed alone. There could be as many rogue planets as stars, maybe more. They're stealthy in the dark between systems. We catch them via microlensing and rare direct images. Some may retain atmospheres, internal heat, even subsurface oceans. Weird candidates for habitability that rewrite the idea planets must orbit suns. TRAPPIST. One is a compact family of 7 Earth-sized worlds orbiting a dim red dwarf so close that from one, a neighbor could blaze like a bright star. Several sit in the habitable zone where liquid water could exist, but red dwarfs' flare and tidal locking complicate life. JWST and future telescopes are racing to read atmospheres and hunt biosignatures. Our most tantalizing nearby lab for, could life exist on an Earth-sized world? Time isn't universal. Where gravity is intense or speeds approach light, time slows relative to outside observers. Consider a thought experiment. Hover near a black hole's horizon. You feel minutes while faraway observers age years. Relativity in action. This isn't just theory. GPS must correct for relativistic time dilation. Subtle daily extreme near compact objects and at relativistic speeds, simultaneity breaks down. It's a mind-bender. Age differences from gravity and speed are real and profound. Some exoplanets melt your expectations. On WASP-76b, iron vaporizes on the day side and condenses as rain on the cooler night side. On other ultra-hot worlds, silica vapor forms glass and blasts sideways, even shards, in supersonic winds. These aren't sci-fi scenes. Models and spectra back them up. Winds hit thousands of kilometers per hour and day-night contrasts turn skies into chemical factories. The diversity of exoweather is a constant reminder. Earth's weather is one tiny corner of cosmic meteorology. Water and organic molecules exist all over, in protoplanetary disks, interstellar clouds, comets, and even exoplanet atmospheres. JWST and others see water vapor and carbon chemistry in young systems, meaning life's raw ingredients are widespread. Complex organics form on icy grains and in shocks, becoming building blocks planets inherit. Explaining Earth's oceans and showing water is a likely outcome of star and planet formation. FRBs are millisecond radio flashes from faraway galaxies, appearing randomly and phenomenally bright. Some repeat, others are one-offs, and no single explanation fits all. Hypotheses range from magnetar flares to neutron star collisions to exotic tech speculations, but many localizations tie FRBs to magnetars in active regions. Their bright, brief nature makes them perfect beacons and puzzles. We use dispersion to probe intergalactic electron density, turning mystery into a tool as repeats and hosts pile up. The cosmic microwave background is the Big Bang's afterglow, a 13.8 billion-year-old snapshot when the universe was 380,000 years old. It's the oldest light we can see, with tiny temperature ripples that seeded galaxies, clusters, and voids. CMB maps from COBE, WMAP, and Planck turned cosmology precise, measuring age, composition, and near-flat curvature. It's the universe's baby picture, scientific gold. Galaxies rotate and lenses bend light in ways demanding unseen mass, dark matter. Galaxies act wrapped in massive invisible halos that dominate mass budgets. Visible stars are icing on a dark matter cake. Direct detection is elusive, but its gravitational fingerprints are everywhere, shaping structure and galaxy evolution. In 1998, we learned expansion is accelerating, driven by dark energy, pushing space apart, changing the universe's fate. We measure it with supernova distances, baryon acoustic oscillations, and the CMB, yet its nature is unknown. It's about 70% of the universe. The universe isn't coasting, it's being actively pulled apart. Voyager 1 and 2 carry golden records, time capsules with sounds, images, and greetings from Earth, hurtling into interstellar space. Neutrinos, nearly massless ghosts, stream through everything, giving a direct line into stellar cores and supernovae. SN 1987A's neutrinos arrived hours before light. Now IceCube catches high-energy neutrinos from cosmic accelerators, messengers light can't match. The elements that build planets and people come from stars, hydrogen and helium from the Big Bang. Heavier elements forged in stellar cores, scattered by supernovae and neutron star mergers. Carbon, oxygen, iron, the stuff of life and bones, cooked in older stars, sprinkled into nurseries. GW 17-01718 showed mergers make heavy elements, gold and platinum. When I say we're stardust, I mean it chemically. Your atoms were once parts of stars, a cosmic family tree linking you to ancient explosions. Biosignatures, technosignatures, the real possibility of life nearby. We're searching for atmospheric gases, weird chemical imbalances, and potential technotraces. Narrowband radio and laser flashes are on the menu. Clues could point to microbial life next door, or engineered activity from distant civilizations. It's an expanding search blending astronomy, chemistry, and a bit of imagination. The real possibility we're not alone drives new experiments and telescopes. You just toured 20 cosmic jaw-droppers, from bending space-time to glass rain, from newborn galaxies to particles whispering through Earth. Let it change how you see everything. The night sky isn't empty. It's a living archive, a laboratory, and our larger home. Subscribe for more deep dives. Until next time, stay curious and keep looking up.